Greetings. In this video, we're going to introduce the basic fundamental of radicals that you're going to need to know for exam number 3. This will include things like the index and radicand. We will simplify our radicals, and we can do so using the product rule, the quotient rule, and we'll take a look at a very specific radical identity that you will be using consistently throughout this exam. So what I would like to do is take a look at 14 different problems and then simplify all 14 problems and then explain how we simplify them using our rules or identities. One other thing that we should look at is the schedule for exam number 3. So just by coming to our Blackboard page, you will be automatically taken to the schedule for exam number 3. Make sure that you know which topics are coming up and make sure that you're trying to stay on time. One thing you can do that will help you out is come down to Module 3 handouts. And if you click on this, you'll run into Module 3, Concepts and Equations for Radicals and Complex Numbers. If you were to go ahead and click and download that, that will give you a document that will group all of our concepts and equations that you're going to need to know for exam number 3 in one convenient location. Now, it's not required and it will not need to be turned in or anything like that for points. It's just a helpful piece of information for you to have next to you as you work through this particular exam. All right, so once again, let's go ahead and take a look at these 14 problems, and we will run down and show how to do this. So the first thing that you absolutely need to do in order to get comfortable with radicals is understand the parts of a radical. So the radical is what most people think of like a square root symbol looks like, but it's the actual radical itself. Underneath the radical is the first term that you just need to know, and that is the radicand. So anything under a radical is called the radicand. And then finally, we have a little number that is outside the radical. This is called the index. This will tell us what root we are dealing with. So you can have a square root. So the number would be 2 or not visible, and I'll talk about that in a second. 3 would be a cubed root, 4 would be a fourth root, etc., all the way up. And we can continue to count up positively with positive integers. So make sure that you understand the index and the radicand before you get started, because those are terms you're going to hear constantly throughout my lecture and any other lecture, and if you read the ebook. Next, we're also going to talk about the product, the quotient rule, and our radical identity that is going to allow us to simplify certain radicals. So first things first, let's just get comfortable with actually talking about radicals. So let's take a look at our very first problem here. We have the cubed root of 8. So what we want to do is understand this problem. So we see we got the little number on the outside that is our index. So we can say this radical has an index of 3. It is a cubed root. And underneath we have our radicand, which is 8. So how we want to deal with radicals is ask ourselves one very simple question. What number multiplied by itself, and then we take a look at the index, in this case it's 3, so we would say what number multiplied by itself 3 times gives us our radicand. So one thing that we could do is rationalize that 8 is nothing more than 2 times 2 times 2. 2 times 2 times 2 is in fact 8, so this is just another way to write it. And then here we can actually write this in exponential form. This would be the cubed root of 2 cubed. So what number multiplied by itself 3 times gives us the radicand of 8? That number would in fact be 2. 2 times 2 times 2, or 2 times itself 3 times, is in fact 8. So there's many ways that you can do this, by the way. Something like the cubed root of 8, you don't need to show your work. You can actually just say that is 2. The cubed root of 8 is 2. Otherwise, you can show your work by using products, multiplication like we see here, or we can write it in terms of an exponent. And this way is going to actually be very helpful for later in this particular lecture, because this is our radical identity. And this particular radical identity we will be using a lot in this exam. So as long as we're here, let's talk about this. This radical identity you just need to know because you're going to use it all the time. What it says is if I've got a radical and its power is the same as the index, we will get to cancel the radical, in other words, get rid of the radical, cancel the power, get rid of that power, and then what is left in the radicand becomes our answer. And this will actually show how we can get negative numbers under an even index, even though you're not supposed to with even indexes. But the point is, this is how this identity works. If your power matches your index, you get to get rid of the radical, get rid of the power, and then whatever is left in your radicand is your answer, positive or negative. So the reason I'm saying this is if we come back up here and take a look how we wrote this in terms of an exponent, my power matches my index, we're allowed to use this radical identity. That says we cancel the radical, cancel the power, and then whatever is left in the radicand is our answer. And sure enough, we can see our answer is 2. So again, this is something you can do in your head, but I'm showing you mathematically why we actually get this answer, because there's going to be problems coming up here that we cannot do in our head. So here is the basic idea of what a radical is. We have an index of 3 and a radicand of 8. We ask ourselves one question. What number multiplied by itself, and in this case, you look at the index, it's a 3. So 3 times, what number multiplied by itself 3 times gives us the radicand of 8? That would be 2. 2 times 2 times 2, or 2 cubed, is 8. All right, so let's take a look at problem number 2. And this one, again, is something that we can very quickly do in our head. This is the square root of 49. Hopefully, all of you understand our answer here is 7. But why is it 7? Well, in this particular case, we get to ask ourselves the same question we did in the first problem. So we look and we don't see an index here. So what that means is if our radical does not have a number written for the index, it is implied to be 2. So once again, if we take a look at a radical and there is no number written for an index, it is always implied that index is actually a 2. We just don't write it. So in this case, we can ask ourselves that question. What number multiplied, and again, we look at the index, this time it's a 2, so what number multiplied by itself 2 times gives us 49? Well, in that case, that would be 7. So in this particular case, that would just be 7 times 7, or we could also write that as an exponent, which in this case would be 7 squared. So again, if there is nothing written here, it would still imply to be a 2. So what I could say is my power matches my index of 2. We can use our radical identity that says if my power matches my index, we get rid of the radical, we get rid of the power, and whatever is left in the radicand is our answer. And once again, this very obvious answer of 7 can be shown in 3 different ways. All right. Let's take a look at number 3. So here we've got negative 3 square roots of 81. I know it's a square root. Why? Because there is no index written. So therefore it's implied to be a 2. So one thing that we absolutely need to understand about radicals is all radicals are exponents. That means you have to follow the order of operations. So hopefully remember the order of operations. Please excuse my dear Aunt Sally. That says we do anything in grouping symbols first, then we do exponents, then we do multiplication or division, whatever comes first, left to right, and then finally we do addition or subtraction, whatever comes first, left to right. But notice we must do exponents before we do multiplication. So in this particular case, when I take a look at my problem, we have negative 3 times the square root of 81. This is multiplication. This is an exponent. You must do the exponent first. And it's not like you could distribute this through anyway, because once again, we have to follow the order of operations. So here, we can simply ask ourselves, what number multiplied by itself 2 times gives me 81? Well, that's going to be 9. So what we can do is just do this first exponent. This becomes negative 3 times 9. And then here, these are just integers. Negative 3 times positive 9 gives us negative 27. All right, So now let's take a look to see what happens when we have variables under a radical. And it turns out variables are actually a lot easier to work with than numbers, because numbers we're going to have to find factors. With variables, we're always going to see the exponent written, and that's just going to tell us how many of this variable we have. So here for number 4, we have the square root of x squared. So once again, what this is saying is because it's x squared, exponents are repeated multiplication. This is just x times x. So when we write x times x, we get x squared, and look what we have. My power matches my index, and again, if there's no index written, it's implied to be a 2. So here we can immediately use, my radical identity that says if my power matches my index, we cancel the radical, we cancel the power, and we're left with just the radicand. So this works for variables as well. My power matches my index, we get rid of the radical, we get rid of the power, and we're left with just the radicand. So here, my answer would be x. All right, and if we take a look at number 5, we can actually do the exact same thing. We have the cubed root of x cubed, and we would have, instead of 2 x's this time, we have 3 x's. This is x times x times x. We can write that as x cubed. But once again, I see that my power matches my index. We get to use this radical identity. If your power matches your index, you get rid of the radical, you get rid of the power, and what's left in your radicand is your answer. So our answer here is just x. So here is how we deal with the fundamentals of our radicals. So now what we want to do is start taking a look at non-perfect square, cubed, or fourth power radicals. So that's what we see here in number 6. For number 6, we have got the square root of 8. Now, we'd ask ourselves what number multiplied by itself 2 times the index gives us the radicand of 8. In this case, we actually don't have a number. If we have 4, that would be 2 squared. If we had 9, that would be 3 squared. But 8 lies somewhere in between. So if you pulled out your calculator, you're just going to get a long string of decimals. In this class, very rarely are we actually going to give our answers as a decimal number, only in specific application problems. Otherwise, we're going to ask for what are called exact answers, and that can be explained very quickly. So an exact answer would be something like pi. We all know pi to be approximately 3.14, but that is an approximation. And even if we went a little further, 15926, there's still more decimal points that we're not covering. So here, this would just be an approximation of this number because this number, these decimals, go on forever without repeating. So how can we write the exact answer of pi? It is the actual symbol itself. So here's an example for you again. The square root of 2. If you plug that into your calculator, you're going to get approximately 1.414. And again, there's going to be a lot of decimals. This is an approximated number. So how can we write the square root of 2 as an exact answer? It's literally the square root of 2. So when I tell you I'm looking for exact answers, I'm telling you to keep them in radical form. So let's go back to number 6. So here, I don't know the square root of 8, but we can still simplify this down. And what we're going to do is use our first rule, the product rule. So the product rule says, if I have got one radical, so I know it says a times b, but that can just be a number. If I have one radical, I'm allowed to break this up into as many products of radicals of the same index that I would like. So once again, what it's saying here is I can take one radical and break it up into a bunch of radicals. It does not have to be 2. It can continue infinitely. So what we can do here is say that I can take the square root of 8 and we can use the product rule that says I can take that square root of 8 and I can actually split it up into multiple radicals that are being multiplied together. The only rule that we need is that the index needs to be the same. So that means here I can take the square root of 8 and break it up into two radicals. So I can use two products of 8, two numbers times two integer numbers that when you multiply them together gives you 8, and we know the square root of one of those, which that would be the square root of 4 times the square root of 2. So in this particular case, we're using the product rule that says I can take one radical and break it up into multiple radicals. I took the square root of 8, found two factors of 8 that I know the square root of one of those. I do not know the square root of 2, and it needs to be the exact answer, but we can simplify the square root of 4. So here, the final simplified answer would be 2 square roots of 2. The square root of 4, what number times itself 2 times gives us 4, is 2. And then the exact answer of the square root of 2 is the square root of 2. So here, the square root of 8 breaks down into 2 square roots of 2. And again, this is what is called an exact answer. Most of the time on the exam, you're going to have to give exact answers. All right. So let's go ahead and take a look at number 7. Here, we've got the square root of 3 times the square root of 6. So by themselves, we don't know these square roots. I do not know the square root of 3, and I do not know the square root of 6, but that doesn't mean we can't simplify. Here, they are being multiplied together, so what we can do is use the product rule. When you are dealing with a math class, and this goes for anyone that's going to go on to higher level maths, when you're given an equation or a formula that has an equal sign in it, you need to know how to read it from left to right and from right to left. So what do I mean by that? Let's take a look at our product rule. This says from left to right, I can take one radical and break it up into as many radicals as I want. But we can actually read this in the other direction. If I've got multiple radicals that are being multiplied together and they have the same index, I'm allowed to combine them under one radical using multiplication, where we would multiply our radicands. So one more time, I can take two radicals that have the same index that are being multiplied and combine them into one radical. So that's exactly what we're going to do for number 7. We're going to read this from right to left. I have two radicals that have the same index. If there's nothing written, it's implied to be a 2. So this means I can combine these under one radical with the same index of 2. And then here, this would be 3 times 6, or simply the square root of 18. But again, I don't know the square root of 18, but we can simplify this. So now what I can do is go right back in the other direction with the product rule. This says if I've got one radical, I can break it up into many radicals. So what I can do is find two factors of 18 that we know the square root of one of those factors. And those factors would be the square root of 9 and the square root of 2. The reason we would do this is because now we can simplify the square root of 9. This becomes 3 square roots of 2, and that would be the exact answer. So once again, when it comes to radicals, it's going to take a little bit of time to get used to, but once you understand the rules and how you can go back and forth with them, it actually gets a lot easier. As always, you just need to make sure that you practice, specifically for this exam, because if you're not really comfortable with radicals, it's going to make this entire exam very difficult. All right, so let's get back to more problems. Let's take a look at example number 8. Here we get the square root of x to the 6th. So one thing that you're going to need to do and make sure that you understand is how to simplify radicals. And in this case, we have 4 different rules that we need to follow. One of the rules says, if a power in my radicand is equal to or greater than my index, it is not simplified. So here 6 is greater than 2. This is not simplified. So what we're going to need to do is use the product rule and take one radical and break it up into multiple. So what I can do, and this is why I say we are going to exploit this radical identity a lot, so make sure you pay attention and understand how to do it, because you're going to be using this a lot. We want to break this up using our radical identity and the product rule. So the product rule says I can take this and split this up into as many radicals as I want through multiplication. But if I can group these factors together such that my power will match my index, we can use this radical identity that gets rid of our radical. So what do I mean here? I see that I have got an index of 2. That means if I want to use this radical identity, my power on my radicand needs to match my index. So here I just need powers of 2 to match my index of 2. So because I've got x to the 6th power, this is 6x, we are going to group our x's in groups of 2. That will match our index. If this was a cubed root, we would group them in groups of 3. If this was a 4th root, we'd group them in groups of 4, and so on. So I'm going to use the product rule, take one radical and break it up into many using multiplication with the same index, and I'm going to get the square root of x squared times the square root of x squared times the square root of x squared. So once again, I can do this using the product rule, but the reason I'm using x squared is now we can use our radical identity. If my power matches my index, we get rid of the radical, we get rid of the power. Well, I have that here, here, and here. So once again, I'm going to use my radical identity. My power matches my index. We get rid of the radical, get rid of the power, get rid of the radical, get rid of the radical and the power, and we're simply just left with what is in the radicand. And in this case, this would just be x times x times x, and then we can group these together using exponents. This is just x cubed. So this would be the final simplified answer that we need. So one more time, if you have a power in your radicand that is either equal to or greater than your index, you must simplify that radical. All right, so let's go ahead and continue on. Let's take a look at number 9. For number 9, we are given the cubed root of 54. So once again, we could ask ourselves what number multiplied by itself 3 times would give us the radicand of 54? We don't know that number. So what we need to do is use the product rule, where we're going to break this up into 2 factors where we know the cubed root of one of the factors. So it's going to be helpful to know some of your basic squares in this particular exam. We're going to be looking for particular factors. Factors like 4, 9, 16, 25, 36, any perfect square for square roots. Well, the same thing will hold true when we're talking about cubed roots. So that means we need to look for perfect cubes. In this exam, you're going to be looking for 2 specific numbers whenever you have cubed roots. Those numbers are going to be 8 and 27. So that means when we are trying to break down a number under a cubed root, the 2 factors you want to be looking for are going to be 8 and 27. So here, 54 is the same as 27 times 2. Those are the 2 factors we need. So I'm going to use the product rule and break this up into multiple radicals. So this is the same thing as the cubed root of 27, something I do know the cubed root of, times the cubed root of 2. 27 times 2 is 54. So once again, the reason we would do this is what number multiplied by itself 3 times gives us 27? That turns out to be 3. 3 times 3 times 3 is 27. So the cubed root of 27 is simply just 3. But we don't know the cubed root of 2, so we leave that as the exact answer. And this would be our final simplified answer, 3 cubed roots of 2. So once again, whenever we have numbers under a cubed root, there are only going to be 2 factors that we're really going to look for. There are more. Don't get me wrong. There's actually more. Any cubed. So that'd be 2 cubed, 3 cubed, 4 cubed, etc. But in this class, those are the 2 numbers that are going to pop up 99% of the time. So you want to look for factors of 8 and 27 whenever we are dealing with cubed roots. All right. let's go ahead and start doing some problems that are going to be very much like your homework and what you're going to have to do for the exam. Here, let's take a look at number 10. For number 10, we are given the square root of 24x cubed y to the fifth. So once again, what we need to do is simplify this problem. So what we're going to do is recognize we can use the product rule to break this up. And then because my powers inside are bigger than my index, I know I'm going to have to simplify them using the radical identity. So what you should always do first when it comes to breaking up radicals using the product rule is break it up into its coefficient and then each individual variable. So what do I mean by that? We're going to use the product rule to break one radical into as many as we want using multiplication. I'm going to break this up into its coefficient and then each individual variable. This is the same as the square root of 24 times the square root of x cubed times the square root of y to the fifth. And the reason we would do this is it just makes it a little easier to break down. So I do not know the square root of 24, so what we need to do is look for two factors of 24 where we do know the square root of one of those factors. In this case, those two factors will be 4 and 6. 4 times 6 is 24. We know the square root of 4. So what I'm going to do is now take this radical and once again use the product rule to break this up into multiple radicals. I can take the square root of 24 and rewrite this as the square root of 4 times the square root of 6. Let's move on to the square root of x cubed. Once again, because I notice the power is greater than my index, we need to use our radical identity. So because I have 3 x's, I'm going to group them together such that it matches my index of 2. So I'm going to group these in groups of 2, but we only have 3 of them. So I'm going to use the product rule to break up the square root of x cubed into multiple radicals. So this is going to be the square root of x squared, because again, I want my power to match my index. That's 2 of the 3 x's we need, but we only have 1 more x. So that means here we will be left with the square root of just x to the first power. So that means when it comes time to simplifying, we actually cannot use our radical identity on the square root of x because we need the same power as the index. Here, my power is 1, my index is 2. So let's go ahead and do the same thing for the square root of y to the fifth. We have 5 y's. I'm going to group them together to match my index, so we're going to group them in 2's. This, we can break down the square root of y to the fifth as the square root of y squared times the square root of y squared. That's 4 of our 5 y's, but we still have 1 left over. So we will get the square root of 1 y. And the same thing here. We won't be able to use our identity because my power does not match my index. So now that we've done this, we want to go through and see if we can simplify. We know the square root of 4. That is simply just 2. I do not know the square root of 6, and I don't know the square root of its factors, 2 and 3, so we just leave this as an exact answer, the square root of 6. Here we get the square root of x squared. We can use our radical identity. If my power matches my index, we get rid of the radical, we get rid of the power, we're left with just the radicand. So this, the square root of x squared, becomes x. But then here I have the square root of x. We do not have enough powers to match the index, so we must leave this alone as the exact answer. So this is multiplied by the square root of x. Here we have the square root of y squared, and here we have the square root of y squared. We can use our radical identity. If my power matches my index, get rid of the radical, get rid of the power, and we're left with just the radicands. So we're going to be left with y times y. And then one final time, we have the square root of y. We don't have enough powers to match the index, so we leave it alone as the exact answer. So this is just the square root of y. Now what you want to do is do some organization. All of this is multiplication. There is no plus or minus signs in here. So what that means is we can use the commutative property and just rearrange each one of these factors. So what we want to do is anywhere we have repeated multiplication, we want to use our exponents. And any radicals that we have in our problem, we're going to throw them at the end. So what I'm saying here is we're going to take the square root of 6, the square root of x, and the square root of y, and we're just going to push them all the way to the end of the problem. And then we're going to clean up what we have left. So what we have left is 2 times x times y. That is 2xy squared. But then we have the square root of 6 times the square root of x times the square root of y. So just when you think you've done enough simplification, there's still more to go. So what we need to do now is go back to our product rule and use it in the other direction. That says if I have multiple radicals, and again, it can be more than 2, it can be infinitely many, that have the same index and we're multiplying them together, we can combine them under one radical. That is exactly what we have here. We have 3 radicals all to the same index that are being multiplied. We can use the product rule from right to left, and we can combine these under one radical. So our final simplified answer is 2xy squared square root of 6xy. So again, simplification with our radicals is definitely a tougher concept only because there's so much more that you need to do. But just like anything else in math, the more you get used to it and the more you just do it again and again and again, the faster that it actually becomes. So make sure that you are constantly practicing to get ready for this exam. This is where the turning point in our semester really begins. From here, all of the assignments, all of the exams are going to come up on you very quickly. So you compensate by putting a substantial amount of time and work into practicing your problems. All right, so let's go ahead and continue on. Let's take a look at problem number 11. For problem number 11, we have got the cubed root of 27 over 8. So what we see here is we have a fraction under a radical. Anytime we see fractions and radicals together, your initial thought needs to be thinking, we need to go and use the quotient rule. So the quotient rule says if I have got one fraction under a radical, we are allowed to break this up into 2 radicals with the same index, one in the numerator, one in the denominator. So the first thing you really should always do in a problem like this, if we've already got, this fraction under a radical, see if you can simplify this fraction. So here 27 is just 3 cubed, 8 is just 2 cubed. We don't have any matching factors, so this can't be simplified. So again, we see a fraction under a radical. That is your clue. We need to use the quotient rule. So the quotient rule says if I've got a fraction under a radical, we can break this up into 2 radicals with the same index, one in the numerator, one in the denominator. So here, we'll break this up into the cubed root of 27 in my numerator, all over the cubed root of 8 in my denominator. Make sure that your index goes with it. We never change the index. So this is helpful because we happen to know these cubed roots. So this is why I said there are going to be 2 factors of cubed roots that you're going to be looking for, and those 2 cubed roots are going to be 27 and 8. What number multiplied by itself 3 times is 27? That is 3. 3 times 3 times 3 is 27. What number multiplied by itself 3 times is 8? That is 2. 2 times 2 times 2 is 8. So here, the cubed root of 27 over 8 is actually 3/2. Let's take a look at number 12. Here we've got the square root of 24 all over the square root of 3. So once again, I see radicals in a fraction. That immediately should jump to your head that we need to use the quotient rule. Because even though I can use the product rule on the square root of 24, well, we actually did that in a previous problem. We got 2 square roots of 6 divided by the square root of 3. It's not simplified. You're going to learn we're not allowed to have a radical in our denominator. So instead, anytime we see radicals and fractions together, you need to immediately think the quotient rule. So what we can do is use the quotient rule, reading it from right to left. I can't stress this enough. You need to know how to read these equations from left to right and right to left. So this says if I've got two radicals, one in my numerator, one in my denominator, with the same index, we can combine them under one radical. So here, that's exactly what we can do. I don't know the square root of 24. I don't know the square root of 3. Let's combine this using the quotient rule under one radical, and we get 24 divided by 3. Now, the reason we would do this is just as I set up here. If we've already got the fraction under a radical, we should look to simplify. Here, we can. 24 and 3 are both divisible by 3. So in this particular case, 3 goes into 24, which would be 8 times. And 3 goes into 3, which would be 1 time. So what we actually end up with, and I should not have actually done this, in fact, before I jump ahead, we want to make sure we understand that's eventually what it's going to become, but this is still sitting under one radical. So again, I apologize, I am jumping ahead here. So once we actually simplify this fraction, we simply just get 8 over 1, and anything divided by 1 is itself. So in this particular case, this is just the same as the square root of 8. So what we need to do now is understand, okay, I don't know the square root of 8, but we can find two factors and then break this up into two radicals using our product rule and simplify. Once again, those two factors of 8 are going to be the square root of 4 and the square root of 2. Once again, using the product rule to break one radical into multiple radicals. And here we know the square root of 4 to be 2. We don't know the square root of 2. So here we get a final simplified answer of 2 square roots of 2. So once again, if we ever see a fraction under a radical, or we see radicals that are on a fraction, numerator and denominator, your mind needs to immediately think, quotient rule, because we're going to see a problem here that is going to be very, very difficult to do if you don't use the quotient rule first. All right, so let's take a look at problem number 13. So here we have the cubed root of 54x to the 4th all over the cubed root of 2x. So once again, we can see that I could use the product rule up top, and that's going to give me something, but we're going to be left with this radical in our denominator. So what you need to do is recognize, okay, we've got radicals in a fraction. We should be thinking the quotient rule. So that's exactly what we're going to do. We're going to read this from right to left. I can take one radical in my numerator and denominator that have the same index and combine them under one radical. So here I can rewrite this as the cubed root of 54x to the 4th divided by 2x. And the reason this is helpful is because now we can actually simplify what's in this radical. So 54 divided by 2 is just 27. But then I notice I've got 4 factors of x on top, 1 factor of x on the bottom. We can cancel 1 factor of x. So we'll be left with x cubed up top. Down below, 1 times 1 is 1. Anything divided by 1 is itself. So what we end up with is the cubed root of 27x cubed. Now, if we decided to do the product rule first, you would end up with a colossal mess. Now, you can still get to the answer that way, but it is going to be frustratingly hard. So make sure you understand where to use the quotient rule because it's going to be very important. Down below, this is not simplified. I know that, first of all, because I know the cubed root of 27. We're only looking for 8 and 27 when it is an index of 3. And my power matches my index. So what I can do is use the product rule to break this up into two radicals. The cubed root of 27 times the cubed root of x cubed. And here we know the cubed root of 27. What number multiplied by itself 3 times is 27? Well, that's 3 itself. So that means the cubed root of 27 is just 3. And then here, the cubed root of x cubed, we can use our radical identity. My power matches my index. We get rid of the radical, we get rid of the power, and what is left in my radicand is our answer. So here, this simplifies down to 3x. So make sure you understand your product rule and your quotient rule, as you're going to be using that a lot to simplify your radicals. And the same thing with this radical identity. There are a couple more that we're going to have to deal with, but you are going to be using this the most. Make sure you understand if your power matches your index, whatever is left in your radicand is your answer. And that could be positive or negative numbers. So let's take a look at our final problem here. Number 14. This is along the caliber of what you're going to see in your homework and on your exams. So here for number 14, we are given in my numerator the square root of 16x to the 5th, y to the 5th, z to the 6th. And then in my denominator, we have got the square root of 2xy squared z cubed. So once again, the point is we need to simplify this, and we see radicals in a fraction. That needs to be your clue that, hey, we need to use the quotient rule. So that's exactly what we're going to do. We're going to read this from right to left. I can take one radical in my numerator and denominator with the same index and combine them under one radical. So that's the first thing we're going to do here. We're going to combine these two radicals under one radical. So we get one large square root where we get 16x to the 5th, y to the 5th, z to the 6th in the numerator, and we get 2xy squared z cubed in our denominator. The reason we do this is now we can simplify this fraction. 16 on top, 2 on the bottom. They're both divisible by 2. 2 goes into 16 8 times. 2 goes into 2 once. I've got 5 factors of x on top, 1 factor of x on the bottom. We can cancel 1 factor of x. We're going to be left with x to the 4th. We have 2 factors of y on the bottom, 5 on the top. We can cancel 2 of these factors. We're going to be left with y cubed on top. And then here we got 3 factors of z on the bottom, 6 on top. We can cancel 3 factors of z. So we'll be left with z cubed. So the reason this is helpful is now my denominator is simply 1 times 1 times 1 times 1, which is 1, and anything divided by 1 is itself. So what we have left is just the square root of 8 x to the 4th, y cubed, z cubed. And this is going to be much easier to work with than if I decided to try and use the product rule. This would give you a mess if you tried to use the product rule on top, then on bottom, because then you would have to rationalize denominators. Just make sure we understand when we see radicals in a fraction, think the quotient rule. So now what we're going to do is we're going to use the product rule to break this one radical up into multiple pieces. What you should do is break it up into its coefficient and then each individual variable to start. So here, using the product rule, I can break this up into the square root of 8 times the square root of x to the 4th times the square root of y cubed times the square root of z cubed. Now what we're going to do is take a look at each individual radical, and we're going to use the product rule again to break it up. I don't know the square root of 8, but we can use 2 factors of 8 where we do know the square root of 1. So here I can rewrite the square root of 8 as the square root of 4 times the square root of 2. Here we've got the square root of x to the 4th. I want to make sure to use my radical identity because my power is either equal to or greater than my index. So because my index is 2, we're going to group our x's in groups of 2 so we can use our radical identity. So the square root of x to the 4th becomes the square root of x squared times the square root of x squared. That's using all 4 x's. We're going to do the same thing for the square root of y cubed. So this is the same thing as the square root of y squared, but then we only have 1 factor of y left, so it's going to be the square root of y. And then we do the final z cubed here. This will be the same as the square root of z squared times the square root of just 1z. So again, now that we've broken this all down, we can look to simplify each piece. The square root of 4 is simply just 2. I do not know the square root of 2, so we leave that as an exact answer. Here, My power matches my index, so we can cancel the radical, cancel the power, and we can actually do that again for the second one. For the y, we've got the power matching my index, cancel the radical, cancel the power, left with y. But then here we only have the square root of y. We have a power of 1 with an index of 2. We don't have enough factors of y to use this radical identity, so we need to leave this alone. So the final thing we see here is the square root of z. So here, get rid of the radical, get rid of the power. But again, we only have 1 power of z. And we need 2 in order to use this radical identity because it's a square root, so we leave it alone. So what we're left with is x times y times the square root of y times z times the square root of z. Now is when we want to organize. We're going to take any of our radical factors and throw them on the end, and then we will combine any other things through exponents. So what we see is we're going to have 2 times x times y times z. This is 2x squared y z. And then we have the 3 radicals on the end. The square root of 2 times the square root of y times the square root of z. Then again, we need to take the product rule in the other direction and take multiple radicals with the same index that are being multiplied together and combine them under one radical. So our final simplified answer is 2x squared yz times the square root of 2y and z. All right. So again, when it comes to simplifying radicals, it can be a little bit daunting just because if you're not used to radicals, it does seem like there's a lot that you need to remember. But thankfully, once you just commit these to memory and once you play around with it a little bit, it becomes a lot easier. I can't stress this enough, especially for this exam. It's going to be practice, practice, practice. The more that you actually sit down and work with your problems, the better you're going to get at this. At first, it's going to go very slowly because you're just learning how to do it. But over time, it's going to get a little faster and a little faster and a little faster. Don't wait. These exams are going to be coming up a lot faster just because this is an accelerated class. All right, so what we did is we went through all 14 of these problems. If you can do all 14 of these problems, then you should be ready to go on to adding and subtracting radical expressions, and those have their own rules because we need to have what are called like radicals. Like radicals need to have 3 things. The same index, they must have the exact same radicand to the number to the power, and you can see it's celebrating because we have to have the exact same radicand. And then finally, we need to have the same variable to the same powers on the outside of the radical. So that's going to be explained when we add and subtract. But for right now, this was the introduction to all the basic things that you're going to need to know for radicals. So make sure that you practice, practice, practice. Otherwise, coming up, there's a lot more tougher sections, so just make sure that your time management is good. We got through our first proctored exam, so now you've come to both scenarios. You've taken an at-home exam and you've taken a proctored exam. You now know how to do the rest of the exams for the remaining of this semester. So good luck to everyone, and as always, if you're having any problems, don't be afraid to reach out. I can help you pretty much doing the same thing I'm doing here, where I can literally in real time work with you over Zoom or something like that. But as always, if you want to, you can actually text me. We have free tutoring at the college. This is one of our toughest exams by and far, just because if you are not really used to radicals, this can be very daunting, and we only get a week to learn them. So again, do whatever it takes to be successful. You don't have to only use the material we have here. I don't care where you learn this material as long as you learn it. All right, so that's everything I needed to cover in this video. We will see you in the next one.